Hi, Paul. Welcome back.
Hello, great to be here again. Thanks for inviting me.
You have somehow, I don't know why, but you're always working on interesting projects. So the last time, we had a chat about JaxRS, which was
Uh,
transformative, and now something similar is going on with a little bit, reflection, but not on bytecode rather than on source code, right? So something completely different. And GPUs. So I guess you would like to make Minecraft faster, or what, with GPUs?
there's two different categories of GPU compute. One is to render things like Minecraft or Forza,
Hmm. Hmm.
which is a micro, the racing car game, which the
Hmm.
graphics is incredible. Or the other is to actually do computation, non-graphical computation.
Which is interesting story by itself, right? Because the entire gaming industry, from the gaming, something more serious happened, because the entire evolution of the GPUs and the PCs was driven by games.
That's right. Yes.
And now it is back to business. So I would say the entire Nvidia story with the H100 or whatever is just about machine learning, actually, and
Yes.
less gaming. And between there was a little bit Bitcoin mining, but
That's true.
but
Yes.
now it's more reasonable, right? So
Yeah, I think there's a more reasonable use case. NFTs and Bitcoin mining were a bit like, I don't know about that, but this I think the AI thing has a bit more
mhm.
traction than crypto.
Yeah, blockchain was a good idea. Like, I mean, GitHub is a good idea, and Kafka is also very similar. But Bitcoin, okay. But the GPUs is actually as transformative as JaxRS, because back then, Java was said to be, I don't know, slow, and ESB and SOAP, and JaxRS make it more appealing. And right now, if it works well with Babylon, Java could be really interesting language to for AI, right? To be better integrated
Yeah,
with GPU hardware.
yeah, that's one of the goals. It's I view the GPU is a use case of Babylon plus other technologies combined together. So what we're trying to do in the platform is to find the right primitive building blocks that people can build interesting, useful stuff in Java, like leveraging GPUs or other forms of accelerators, without us having to embed that explicitly in the platform itself. So then we provide the building blocks, and everyone can move faster in that sense. So I think in the prior attempt, I think it was Project Sumatra, we tried to do that in Hotspot itself, and it is pretty gnarly problem, and they made good progress. But trying to embed that into the compilers of Hotspot and to get garbage collection working and so forth, it's a real challenge. So if we can provide the primitives that allow developers to write GPU supporting libraries better than they can do today, I think that's a win-win situation. So code reflection enables that better than the existing technologies in the platform. And when you combine that with Project Panama, which allows you to do foreign function integration with native libraries better, the two combined make for a very interesting way to build libraries. So I'm not doing most of that work. That's Gary Frost who's doing that work. So he's leveraging Panama and Babylon and experimenting with a GPU programming model as effectively as a library to help say that sort of Panama and Babylon are fit for purpose, but also provide some value. So we can also work with GPU vendors, hopefully at some point, and then they can sort of collaborate with us, and we can build something really first class.
Mhm. So which buildings block? So the idea of the project Babylon is to have a nice bridge GPUs, right? Between as a bridge between Java and GPUs. This is the main goal, right?
To effectively enable a bridge, GPUs is just one use case. So the what you if you look at GPUs, if you want to code to a GPU, it's a limited sort of programming model, if you like. If you look at CUDA or OpenCL, the programming model is different to what one would ordinarily program for a CPU, and the reason is because you're writing parallel programs. And so the model is constrained. So if you're going to write in Java, not every program makes sense to execute on a GPU, and not every program sort of is designed to, because it's often sequential code. It's not highly parallel, but maybe a small part of your program that takes 99.9% of the time to execute, whatever, the sort of boundary makes sense to run on a GPU, and that is constrained. So the idea is of Project Babylon is we will expose out selected areas of Java code in a sort of model that then you can reason about and then transform to, say, CUDA code or OpenCL. But that's just one use case. So what Gary's doing is designing a GPU programming model that's sort of limited, is constrained, and then he can take the code model he gets out at runtime or at compile time and translate that to CUDA code. But we could also take the model and auto-differentiate it, or we could take the model and auto.
What means auto-differentiated? What does it mean?
Oh, so one thing in machine learning is when you're training machine learning models, you need to differentiate your function. Your machine learning model is just a function, effectively, and you need to differentiate it so you can find the optimal minima that you hope is a local minima. And so you need to differentiate that mathematical function. And so you can, one technique to do that is to analyze the program statically and then apply the rules of differentiation to that program. And so you could do that with a code model as well. So it's really a way to get access to the code in a form that's better than bytecode. It's better than the AST exposed out by the compiler. It's standardized. And it's in a form suitable for this kind of reasoning and analysis. So you don't have to transform it into something. First of all, it should be there, mostly reasonably there to reason about data flow and control flow and stuff like that.
Then in the Babylon world, the model would be the implementation of such a function, right? Or so what it means is we could do the differentiation on the function level, or we can do it deeper on the implementation level, right? So we have two choices.
No, let me try and explain. So you've got a mathematical function written in Java, and you code it in Java, you compile it to bytecode.
Yes.
But also at the same time, a compiler will have compiled it to a different sort of structure, what I'm calling a code model. And when you do the auto differentiation, you will access the code model, and it's effectively in symbolic form, describing the code. And then you would generate a new code model that's a differential of that one, and then you compile that to bytecode. Or you could interpret it. And
so you would without the code model in Java wouldn't be possible, right? Because it would be hard, to analyze bytecode, and the function doesn't provide you enough information of the.
That's correct. In some cases you can, and in other cases it's harder. I think we don't provide in the platform for various reasons access to bytecode directly. If you wanted to access the bytecode off disk through class files, you can do so. But it's often in a form where you've lost information. It's in a stack-based form as well. So often, if people are going to reason about code that's in bytecode, first of all, they might lift it up a little bit into a form that, which is effectively what compilers do. The C2 compiler or Graal compiler will lift it up into a basic block graph form and convert it into something called it's either single static or static single analysis. Static single analysis form. So it's easy to reason about the code. So bytecode is designed really to be consumed by the VM. It's not designed to be really analyzed as such, although you can. And the same for the sort of AST you might get out of a compiler. First of all, it isn't standardized. So the Eclipse compiler has a different API to the Java compiler in OpenJDK, and is very closely aligned to the grammar. So there's a lot of idiosyncrasies, what you call surface syntax details and so forth like that, that get in the way of doing analysis. So we're trying to find a sweet spot between the AST and bytecode where you can do these kinds of analysis, and to make it easier for GPU code, but also for other kinds of code. For example...
this reminds me of two things from conceptual perspective. One is completely different, but similar from conceptual perspective, is in GraalVM the truffle. This is like the meta thing where languages can talk to each other, but this is more like API. This is not like the model, like the data, right? It's more like just, the ability to talk to each other. And the other thing is, a long time ago, I spent time with model-driven architecture, MDA. And there were two models. One was called PIM, Platform Independent Model, and the other one was the Platform Specific Model, PSM. And the attempt was, to have a state machine and the interfaces, and to specify something on the higher level. and generate, from the metadata, which was in the MOF meta object facility was called, I think, to generate, different representations. And the code model seems to me to be similar. So you have like an easier to use, to consume bytecode representation, right? Which can be then output, or how to call it, transformed to different things. Yes. And one, what should be really interesting, would be WASM or something like this, right? So
you could do that. You again, a constrained programming model. You could compile it down to WASM. I think trying to compile Java in general to WASM has challenges.
Yes.
You have to emulate the runtime, but if you're willing to deviate from the sort of specification of what Java gives you and say, I am now going to infer this program in my own way, even though it's syntactically correct Java code, then you could do that. Just like CUDA code, the same concept in a sense. Just back to those two analogies, I think Truffle is effectively, when you write a Truffle compiler, you're implementing an AST interpreter that then gets recompiled by the Graal compiler. It's quite clever. This is meta-circularity. Whereas where the connection would fit is you could write a Truffle interpreter for the code model, just like you can write a Truffle interpreter for bytecode if you wanted to. So,
but this is even crazier. So you can run the code model on the Graal VM.
If someone was willing to write an AST interpreter for the code model, they could do so in that sense. That's the way I'd see it fitting in. Or alternatively, you could transform the code model to Graal IR, just like you could transform it to bytecode, or if you wanted to go C2I. But the real transformation interchange I was interested in when I was looking at this was mid to high level kinds of transformations. And there's this technology called MLIR, which I think stands for mid-level IR, intermediate representation, developed by Chris Latner. And he was doing all these sort of GPU coding. He was looking at LLVM and saying, this is too low level to do machine learning type technology. It needs something higher level where we can reason about the transformations at a higher level and then lower it down progressively to my target execution environment. Because once you get to LLVM bitcode, it's too low level to reason about loops and types of memory accesses if you can reason about it at a higher level of what's going on. So that's where I thought, well, if we provide a similar type of abstraction in Java, in the Java way, but it's a short hop to MLIR compilers and toolchains, then we can leverage all this interesting stuff that's done out there. And
Chris Latner is interesting because he created Swift and Mojo as well. This is like,
that's right. He's very ambitious endeavor, Mojo. We'll see if anyone can pull it off.
Yes.
There's very few people who could pull that off. He may be one of them that can do it, I think.
Because I always wondered, right? Because it's two interesting stuff you are speaking. So I had to know wanted to mention something, but your stuff is too interesting. So I'm just thinking what you said, because there's a complete different opportunities and possibilities. But what I wanted to know, Python, it comes with low performance. So this is orders of magnitude slower than everything. This is actually why Chris Latner also created Mojo to speed up Python. But I always wondered, right? Not wondered, but the fact right now. So if the AI becomes more popular, the challenge is not to use it. The challenge is to integrate it in existing applications or enterprise applications and use it, right?
Yes.
And then whatever we did back then. So I'm right now after the live streaming show, and I got the question, what about optimistic logs and transactions and databases? So we get the same questions, asked in model. Are the model concurrent? Yes or no? How much transactions we can ask the model in parallel. Does the model run in one machine or not? So the entire integration becomes more and more challenging, I would say, because I don't think it is enough just to call ChatGPT via HTTP, because lots of companies say it is not with us, right? We would like to run everything on our machines.
Right.
So there will be at least some challenges, and I would say Java is actually perfectly suited for it, because I already thought if nothing happens in Java, we could at least use GraalVM, try to run Python in GraalVM, and try to communicate efficiently with Python or whatever, just to hack a little bit. But in your Babylon project, it's really a clean idea how to integrate the model seamlessly And with Graal VM, maybe later, even really fast, right? Because if Graal VM will optimize the entire thing, it will run orders of magnitude faster than Python, right?
My own opinion on this is the Graal compiler compared to the C2 compiler, they're actually fairly comparable in terms of performance overall over a large set of benchmarks. You'll get ones that are better in others than that. So I think there's a couple of advantages to Graal in that it can offer you a polyglot world if that is what you want to operate in, although I think that's quite a niche area. And another niche area would, I think, be the idea of a static compilation ahead of time, so you get the faster startup and potentially smaller memory footprint. But I don't think in and of itself it will speed up the execution of machine learning models compared to C2 like that. I think where we get into that is really identifying areas of code that we can offload to accelerators and giving the libraries the ability to transform that code themselves and letting the platform get out the way for them. So it makes it a simpler problem. It's not a hard problem in general, but if the platform can get out the way and give the information to the library developer in a suitable form, they're far more productive. And if they can rely on that as a standard API, then we get interoperation. So code models can be used to interchange with other libraries. So, you can get these layers of interoperation and transformation going on. So hopefully we can build up a sort of ecosystem around this, which is composable. And that's a real power here, I think, is this building block. And all it is really is just a symbolic representation of code that we think is at the right level for this kinds of use cases. And then if we can provide the right APIs in a simple but powerful APIs to access the model and transform it, people can build their own reasoning on top and really to interchange to other tool chains, whether it be Graal, whether it be MLAR tool chains, or whether it be something like we did an experiment with Oracle Labs. They had this platform called Parallel Graph Analytics, where you can write a Java program, and it will do a query over a very large graph. But that Java program is actually transformed into another kind of program that's executed across many machines. It's never designed to be run as bytecode. And we plugged in, and they were operating at the AST level of the compiler, and we changed it to operate at the code reflection and sort of did a switch between the AST model to the code reflection model and pumped it in through their compiler that way. And it's actually a lot easier for them to go that way. There's less friction to do the other routes. So they're more productive, but they don't have to throw away all their existing code they have to do so it's an interchange problem between various different domains. And I see that playing out for GPUs as well.
So what you said, just because just to catch that, and what you did in Oracle Labs was a Java program was transpiled to how's it called, to not language model, how we call it.
It was so there was this platform called, there's this sort of library platform, if you like, called Parallel Graph Analytics.
And this was the model there, right? So there was the.
So it's a framework, really. It's a framework for writing graph queries, and they have their own way in Java to write a parallel graph algorithm to do queries on graphs, but they plug into the Java compiler to get access to the AST, and then look at the AST, which is effectively a model of the code, a symbolic model, and then transform that using their own compiler toolchain to generate multi-threaded Java code that runs in fork join and runs across many machines.
Cool ideas. Actually, what database also kind of doing, right?
Yeah,
they translate the SQL to machine.
Yes.
Yeah. And the recent Hibernate, I think 6, they also have all the queries in a model. So they switch
That's
from.
right. You build up a query plan. Here's another way we can think about code reflection. You can also model SQL queries. So you have like what LINQ does. LINQ allows you to build up an expression that says this expression can be transformed to an SQL query. And so rather than writing the stringy SQL or something very low level that a compiler would write, you can write at a high level and then transform it into an SQL expression. So it doesn't have to be just GPU code or something like that. It can be something bit more abstract.
So this link language integrated querying.net is a similar idea to the
Right.
code model.
Yes.
Okay.
Yeah, very, very true. So expression trees in C#
Mm-hmm.
are kind of similar to code reflection in Java, except that we're trying to express more code. In expression trees, you can only express a very limited set of C# code, I think, just because they ran out of steam.
This is why C# is able to generate the Wasm, right? I think this is the entire trick.
Maybe they're using something else.
Yeah.
Maybe they're operating at the CLR level for WASM.
Mm-hmm.
I don't think for expression they're not operating at expression trees. They're probably operating at a lower level.
So the code model is your your choice to restrict yourself, right? So this is this is on purpose. We are restricting the power of bytecode to something more precise, maybe, and also limited. And from that,
I say no. It's more. It's expressing more information.
More, okay.
Yes. So it will in a form that's easier to reason about. So, but it will express less information than what's in the AST. So.
Yeah, what I thought, I know there was, for JavaScript, there was a Mozilla project where they did a subset of JavaScript to run faster. I forgot the name, and then Wasm happened. There was, the library. You remember this? This was like.
I can't remember it, but yeah, that could make sense. Yes.
So I thought that the code model is something similar, but it's the opposite is true. So you use the code model, to put usable information on it, but only information which is required. It's more like maybe a state machine almost, right?
Well, it's basically it's a symbolic way of describing your program. That's what it is. So an AST is a symbolic way of describing your program. Bytecode is a symbolic way of describing your program. Source code is for users reading it. And so it's like an intermediate representation, but we're trying not to call it that in a sense. Okay. So that's why it's code model. And model is a very overloaded term, of course, in computer science. But it's really a model of code that is at a certain level where it retains the structure, like the control flow nested structure of code, and it contains the types that may be thrown away when you lower to bytecode. So if you look at this sort of textual form of it, where we can convert a runtime instance in memory to textual form, you can compare it with the Java code one-to-one. So you have this meta model. And in that meta model, you model Java language constructs, and then then it's up to us to decide how many of these Java language constructs do we actually want to model. So you get a high level model, and you can lower it into a low level model if you wanted to, stripping away the structure, but it's still capturing the way the code would be represented by a runtime compiler or a standard GCC compiler. They all do the same stuff. They convert it into basic blocks and static sort of SSA form as well. And so there's various levels you can operate on this to decide how you want to translate to the domain you want to go to, be it a GPU or generating bytecode because you've auto-diffed it or auto-vectorized code. So it's trying to get the sweet spot of the right level of modeling of Java language constructs in a way that you can reason about the code.
Exactly, because what I'm looking at, I think I saw this and it was readable to me. And I'm just, is this the class file API?
No, but the class file API is an API for generating and parsing and transforming bytecode. Although it's very nicely designed API.
Yeah, Java code model. Okay.
Again, model is an overloaded term.
Yeah, but I think I saw on one of your talks, maybe, but there was a text representation of the code model, and it was readable.
Maybe it was in the JVMLS presentation.
Yeah,
and the slides there. There's an example. I show an example, a small.
This is maybe because one of your talks I saw this. It's okay. This looks actually nice, and then I tried to find it. And I searched for code model Java example Babylon, and I found 457 JEP. Interestingly, as this was the third. It was the third hit.
I can send. Actually, I'll send you a link.
And I will put it to the show notes.
Yeah, there's this link here to the and underneath there's a JVMLS presentation, and then there's if you look at the presentation, looking now, there will be it goes through a lot of what I've said here in probably a clearer, more systematic way. And slide 26, there's a few simple examples you'll see of the textual representation of code models, and you'll see it looks very similar to
Exactly. This is, I think, what I saw. I remember the code reflection annotation, and then there is a func and a double with almost lambda example, and it looks readable, right? So it is more readable than bytecode, I would say.
This textual form is really primarily designed for debugging purposes and testing purposes. It's not designed to be written by hand as such, but it's useful to communicate. It's a useful way of communicating what's going on.
And you cannot use bytecode because type information is missing, right? Or what?
In part, sometimes you erase generic types. We also lose, byte types at least in locals. We widen shorter integral types to int, for example. So byte short will get
exactly.
Int. Also, you're dealing with a stack, and when you're dealing with a stack, it's harder to reason about where things are used and not. Stacks are great for interpretation, but when you're trying to reason about code, the first thing I think people would do if they're going to do some serious analysis of bytecode, not just sort of changing this method call to that method call, and so very local, is you would lift it up into basic block form where you've got, and so you understand the control flow, and then you'd lift it up into sort of a value-based form and get rid of the stack so that you can reason about what uses what, because in the stack it's very hard to do that. So you have to sort of interpret running through and get rid of the stack and then build and then connect these blocks together to understand the control flow. And
crazy question. Could you generate from code model Java again, right?
Oh, you can, but you'd lose a bit of information. And you could also generate the code model from bytecode lifting up. So, and in fact, we do tend to explore that too, because if you just have bytecode, lifting it up into this model is actually useful for analysis too. And so it's possible to do that. You can lift it up further, but the challenge is dealing with the control flow. And a great example of this is IntelliJ's Fernflower. It can lift up bytecode to source code, and that is not an easy problem to solve because there's ambiguities, there's weirdness in branching and so forth like that. You have to sort of recover the structure of code. It does a marvelous job, but every time we add a new feature, it has to work out what to do. So it doesn't understand patterns fully or something like this. But
so then Babylon is a success of Sumatra, right? So Sumatra was the first attempt, and Babylon is now rethinking.
In a sense, we're connecting a GPU use case to this in part because we want to solve the GPU problem, and in part we want to make sure Babylon is fit for purpose as well. So we need use cases with Babylon to get feedback and say, well, this worked well, this work didn't, let's change it, and so forth. So it's acting as a use case, but it's also a very important use case independently. And so the aim is, can we write a library that supports GPUs really, really well and defines a good programming model and leverages the features we have in the platform that we're devising? And so it's pretty key use case.
One understanding question, because I always ask myself, so if let's say it is working, so it will work. So we have a Java program and we translate it to code model, and code model gets executed on the GPU. And this is some kind of machine learning stuff, so AI or whatever, right? So then we have actually a very tight integration between Java and GPU, a very low one. I think lower one could be that we just write the CUDA directly, but it is not manageable, I would say, or whatever, right? So this is like whatever. This is a very efficient and fast integration. So if you pick now Python, they also have the chain, how Java, if you compare this technology with currently available Python technology, is it comparable? Would Java be faster, better? This what interests me really, because what they are doing, because
that's right. I think when Python is so malleable in its syntax, and access to APIs, I think if we're going to do the equivalent that what we're trying to do in Java, they would access the Python AST, and they would transform the Python AST. as I don't really know much about that at all in terms of its API, but that's what they would use to access, and they would transform that AST, and they would deal with the looseness of typing in Python to the advantage that they had. You can just add anything to anything; it doesn't matter. It just syntactically it doesn't matter until you get to runtime, and then it finds the types aren't compatible, which is great for writing concise sort of code on tensors, because you can do operator overloading on it. It makes concise code. But I think the equivalent is in Python, you'd operate on the AST, and you would do that. I think operating on the code model design is actually a better way to do this kind of problem than operating on an AST. It's easier for the developer. It doesn't mean the problem in and of itself is easy, but we're just making it easy, less friction, a smoother process to do this. So I think we can do what Python can do, and I think it will encourage people to do what people do on Python today in Java, and make it easier for them to do that. For example, here's an example I've been looking at. OpenAI have this library called Triton, written in Python. You can look it up, search for OpenAI Triton, you'll find the blog post there. And I was reading it recently. And so they have Python. You can write in Python a Triton model in Python code, or a programming model, Triton programming model that's restrictive. It's not all Python code. It's represented to compile down to a GPU, and effectively you code in blocks of tensors, and you can add tensors, multiply them, dot product, do loops, and so forth like this. But it's an easier way to write code that gets executed on an NVIDIA GPU, say, rather than having to directly write CUDA or PTX. So it makes the OpenAI developers doing all their matrix multiply and deep learning stuff more efficient, and they can experiment with more performant algorithms.
So Triton sounds to me like the Mozilla attempts to make JavaScript faster, right? So now just to restrict Python, just to be executable on the GPU.
And in fact, it's bypassing the Python interpreter almost certainly, and it's got their own compiler in, and it's leveraging MLAR to generate the PTX code. So that again, they're looking at the Python code, transforming it into their own model, and then transforming it into MLAR with their own dialect in it, and then pumping it through all of the existing MLAR toolchain that's available. And so I've done the same in Java using code reflection. So I can write a Triton program in Java with an API, and I can generate the equivalent MLAR-like structure that I could then pass over to the existing compiler toolchain. And so I can do the same thing. And of course, I know what's going on. So because I've worked on this and designed a lot of it, I can do it quickly. But then my feeling is the APIs are holding up and in the abilities to do this. And that's encouraging to me that if you can do this in Python, we can do the same in Java in the same way. And I think probably in a better way, at least to get the initial information out, to be able to operate on the code. I think it's in a better form.
Yeah, this answers actually my question, because what I always wondered, what the Python developers are actually doing. So how they interact, with the GPU and how they train the models, because they have to interact, and this GPU is very low level, so that there should be something in between. And the more is in between, the slower Python gets, right? Because you cannot just execute.
Yeah, a lot of the time Python is just a shim around native code.
Yeah, of course. But even then it's even worse, because then there's no more Python. Then Python will look like C, right? So this is what I say.
That's why Chris Latner's created Mojo, I think, in that respect, which is a superset Python. But it is often the libraries, the Python libraries are often a shim around native code. And in fact, we're playing a similar game with Panama. We're saying, well, if you got this very efficient native library with Panama, why not use it? So in combination with Babylon and a transformer written in Java, the speed is not important there. Like in Triton, they've written the Triton compiler in Triton transformer in Python to generate the model, and then they go to the native, and then they just pass it all native. And we'll do something similar, since we need to talk to the native GPU drivers anyway. We need to bind to them. So what we'll do is we'll write the transformers in Java, and to the point at which then we can hand off to the native code. And so Gary's been experimenting with actually lifting up to OpenCL C code from Java code.
Yeah, this is what I thought. because we have compiler, Python doesn't, right? So you have a lots of experience with C2 and with Hotspot. And what you could do is you could try to optimize, how the code model, how it talks, to the hardware almost, right? So you can
optimize the memory. An example of a high level, we want to stick to sort of mid to high level optimizations here, and then let the other tool chains do the like C2 and Graal and that do all of the. If you're going to execute on a CPU, they're super optimized to do this. And so we just need to pass them at a high level. And even for GPU compilers, they've got a lot of optimization. And so if we operate mid to high level, we can look at a call graph. So you might have a GPU program might actually call multiple kernels in loops and so forth. And so the program is sort of a closure over a compute of multiple kernels that call each other. You can trace the sort of ins and outs of the kernels, and you can trace within the kernels where the memory is read or written to. So you can optimize the sort of data movement by looking at the program more globally at a mid to high level. And from that, you can use that strategy to generate more optimal code when you lower it down to your execution target. So that's one thing we're looking at there. I think the key thing for GPUs is the kernel problem is kind of solved in a way. We're just making it easier through Babylon to enable that. What isn't solved so well is the composition of multiple kernels together. So often you'll find like the CPU.
What do you mean by kernel? Is this like a CPU interaction, or?
A kernel would be something that executes on the GPU like a matrix multiply, or add these two big arrays together, something like that. And then you may do multiple kernel calls, multiply this matrix by this, add these two together, then go around a loop and check whether your error condition is of that, no repeat, is a very crude example. So you might have a loop in the CPU guiding and issuing kernel calls to kernels that precompiled for the GPU, and then passing copying memory to and from.
Almost like threads, right, for Java developers?
Yeah, a little bit. They're more asynchronous calls.
Mm-hmm.
You could think of them as asynchronous calls that do something that's not on the host.
And you said the kernel creation is solved. What's not solved is interaction between kernels, or not optimized.
I think kernel creation has been done before in Java, but we can make it easier to do that through Babylon. But I think we can go to the next step and look at compositions of kernel calls as well, and get the code model for the whole call graph of the kernels, and then analyze that as well. And we can make more sort of interesting optimization decisions at that level as well, for how data movement occurs across GPUs, and perhaps split the program out. So if you look at the whole program, you can actually split it out into the GPU bits and into the CPU bits, and then there's async calls between the two, ping-ponging between the two. And so if you have a system.out.println in your host, that will still work, but the GPU bits will go off to the side and be black boxes to the host, and they just be async calls to them. So we can do that kind of.
So you could decide which runs on CPU and GPU, you're saying, right?
Yeah, I think some of it makes sense on the CPU, and some of it makes sense on the GPU. I think devising a programming model where it's very clear what runs where is important. And
ones run anywhere, right? So this is like back to JDK 1.0.
In actual fact, the same thing. What Chris Lattner did with Swift for TensorFlow was very interesting. And what he was trying to do was write machine learning models in Swift and create a TensorFlow model from the Swift code by extracting out the model from the code by doing the analysis at the right level. And I think we can do that using code reflection too. It's an experiment we need to try to see if it works. But we think we can devise an API that allows you to build a machine learning model, express it concisely in Java, not as sort of add mols. When you build up this, effectively, what people do in Java, if they're going to do training often, is to build up a representation of the machine learning model, which is what a compiler would do. So if we can represent it in Java with an API and then pass the code model and then do analysis to extract out the machine learning model from that, we think we can generate Onyx models from Java code. And that's an interesting prospect from designing machine learning APIs. I think it would be a useful experiment to try.
I think this is very useful because it would be like a native integration between Java and machine learning, how to call it, environments or runtimes.
Yeah, I think so. I think we can really push it. And to some extent, Java's behind because there's never been as a focus on machine learning as there has on, say, Python, but you can do a reasonably good job today in Java, and we see some libraries like that, but it's just the focus isn't there. It's not that you can't do it, but we can make it better.
But the focus will be there. I mean, the money is in machine learning right now.
I think so. You had an important point, is that people will want to integrate with their existing systems in the enterprise, and there's a lot of Java code in the enterprise that will want integration, predominantly on inference of machine learning models, I think, more than training. But still, there's that integration in, and we need to make that better and smoother.
Absolutely. And what the next thing is, of course, performance, because if this thing runs in the cloud and Python is 35 times slower than Java, and if I have my high-level Java program, I will have to transform my data to something which is usable by the code model, and it cannot be one-to-one. So my enterprise apps are dealing with JSON, with Java records, high-level representations, and I will have to to transform it and adapt it to your API. So this happens between as well. And if Java runs the entire thing, it will be a lot faster than Python. I mean, this will be at least 2.
Yeah, you can. That's for sure. Most people will not run Python like that at all. I think a lot of it depends, actually. In some kinds of models with inference, you can do it reasonably on the CPU with vectorization, but in other cases, depending on the size, you have to go to a GPU to do it.
Mm-hmm.
And I think allowing that choice of execution target is an interesting one. And if we can enable developers to build libraries to allow for that choice, and Panama and Code Reflection come in to help the developers write those libraries better, I think we'll be in a good position.
Yeah, absolutely. And first, we have also educate developers first, because you don't even know what's possible right now.
No, one thing with this project is I expect to be surprised by people doing really clever, crazy stuff. So I'm hoping that once we go open, I hope we can go open source this month. Intended it to be last month, but we never got there yet. We just missed it. So hopefully we can go open source this month, and then I can write a few articles after that to help guide people and inspire people. And I hope people will just start doing some really interesting stuff with it.
So my estimation is this is one of the most important projects right now. So this is how I see this. And for different points. One is AI, of course. This is where the business is right now. And the questions regarding integration I get, no kidding, if I meet a new customer every time, how to integrate with the ML with our existing Java applications.
Right.
Then if it runs in the cloud and you can run a little bit faster, there is money there, right? The faster it runs, the less you pay, period. So this is huge use case for Java, Java. What I do in the cloud right now, 100% pure Java, just because of costs.
Yes.
So, and because Java is so fast. So it's actually, how to call it, people even don't know how fast Java is. So if works great for serverless for all the use cases, actually. And the next thing is WASM, right? So for the code model, I could also use to generate WASM, which sometimes is interesting, for edge functions, or we could do at least because why I should leave Java? No, I know Java well, so I would also, if I have to create a small WASM thing, I would pick Java. Just try and I'm not willing, to use Rust or C#. Just to output WASM once, right? So I would pick Java.
Yeah, and actually, sorry to interrupt. I don't know a lot about use cases of WASM, but you mentioned sort of edge functions. What do you see going on there?
So what companies are experimenting with is if you have a cloud, but the cloud has so edge servers or edge endpoints, and this is more or less a smaller service, and also servers like a small data center, and then there's a cache, and before the cache is hit, you can run a small function, and sometimes it can be a WASM function, or a stripped down JavaScript.
I see.
And in the full data center, you're running, functions, Java functions. But on the edges, this is usually WASM. And another thing is the Kubernetes community, which right now I'm using more serverless stuff like AWS Lambdas or Azure functions. But in Kubernetes, they're also experimenting right now to use WASM instead of almost like a Docker replacement almost, or in the Docker WASM, like a runtime. So instead of bytecode. So it is WASM is important, but it didn't took off in enterprise, but it could at least have the possibility to, to have an answer is important.
Interesting.
Yeah, really interesting, and it's somehow ignored by the Java community. Also, there are so many places. So if you search for, I think, edge function Wasm, you will find some companies providing services, and there's even, it's called something like Wasm system interface. So they're even providing like almost POSIX compatible API for Wasm that you can call files and stuff like that. So this is this is almost like bytecode, right?
Yes,
but
it is.
but yeah, this is, for me, it is a little bit boring because, okay, we had it 20 years ago, but now what? Now the entire world moved to Wasm, so we have to do something with it, right? So this is a little bit pity.
Well,
but
I think, people who have to conform to the latest ECMAScript standard have to support WASM, I'm presuming, in some form or other. And so it gives, there's sort of, so all browsers effectively probably have to support it. So it gives it another thing to consume rather than just JavaScript.
But in browser, it is less interesting because it cannot interact with the UI, but could, for instance, incorporate machine learning model or whatever, but not, it is more, it's almost like a kernel, what you said, right? So there's Wasm in the browser, you can call it, you can pass byte array, you get byte array back, but you cannot, modify the DOM right now, for instance.
Right. I see. Interesting.
Yeah.
I mean, if you wanted to, if you wrote a Java method and annotated it and you constrained it, you could potentially create a WASM equivalent of it if it's sort of like a kernel-like piece of functionality, but doesn't require sort of like, extensive use of Java APIs, which you'd have to emulate otherwise. On that, if it's something simple, you can almost certainly do that kind of transformation.
And this would be very important because Wasm is limited. It doesn't make sense, to call external APIs, because if it runs in browser, the APIs are not there. So I would say this is...
Yes, it's a challenge. Even using array list might be a challenge, Java util array list or something like that.
This is the same in JavaScript. You have to pass from JavaScript to Wasm some stripped down array in specific, not array list, rather very low level stuff. So this is to expect. The interaction with Wasm is crazy. So it is not fun. So I would say, therefore, it is absolutely okay to put annotations and generate something which is, an island, I see. So this would be enough at the beginning.
Yeah, I think.
And the next thing I wanted to ask you about that, because this is, maybe it doesn't make any sense, but what I'm really looking forward in Java is string templates.
Oh, yeah.
Because they also are almost like a link, because there is an interpreter which, or not interpreter, I don't know what to call it. So it is smarter than, the replacement what we have right now in multi-line string. And you could even, to my understanding, this is not public now, but it knows about the types inside the block, and we could also incorporate it with the code model, right?
Yes, I haven't thought too deeply about that, but it did occur to me. So string templates, so really, you've got this template processor, and you pass it a string template, and what you get is a string with holes and results of the expressions as an object array coming in. And from that, you can do anything stringily. Which is actually quite reasonable in many cases. Even SQL, as long as there's risks that you're going to generate syntactically incorrect SQL statements from that or other things, but it still works very well like that. Now, what if you could actually get the code model for the little expressions that are in the string template? So rather than passing the result of the expression, you get the code model plus the result of the expression, and you may be able to do something interesting in there. I think so. It remains to be seen. We also have to model string templates themselves. So if you had a method that you wanted to get the code model and you had a string template expression in there, we're going to have to model those as well. So we haven't done that either. But string templates are interesting. I think they're wonderful, wonderfully clever design.
Yeah. And I waited for them. What I already wanted to do is, to try to reactivate the Jasper, from Tomcat JSPs for the server. But the string template will solve it. You could actually combine string templates with JAX-RS, and we have the best template engine on earth in Java, I would say. And
I think there's going to be interesting ways people are going to do that. I really like the design that they put this notion of a template processor in, so that this can act as a sort of guard, because as you're doing string work, you want to make sure that someone isn't injecting something into your strings that are going to poison them. And so that was a very important part of the design process to ensure that can actually be controlled by the developer.
At the beginning, you said that Babylon comprises multiple pieces. So one was the Panama, which is like modern GenI. So GenI without C, right? Then what else we have inside?
Well, I wouldn't say code reflection doesn't encompass Panama. I think the two together are kind of like greater than the sum of their parts. So they're independent. So Babylon is the core is giving code to users in a reasonable form, what we're calling code reflection. And there's a use case for the GPU, but Babylon really consists of kind of three things, I would say. Well, first of all, we have to model Java programs as code models, just like the AST models it or bytecode does. We have to model for loops, while loops, arithmetic expressions, string templates, assert statements. And to some extent, we don't know where to draw the line is yet on that first bit. Do we model all programs, or do we only model a subset? Or do we initially only model a subset and then over time in multiple releases expand it out? All questions we still need to determine. But we have a prototype framework to experiment with that. So we model Java programs as code models, and we do that through a meta model. And this model plus meta model sort of is suitable for the sort of analysis and reasoning about code and transformation.
And the meta model describes what was about, right? That we have for loops, that we have whiles, and
even then it doesn't. It describes a more abstract notion of basic blocks connected together.
Okay,
in static single form, and a notion of nesting. And then it's all operations, and the operations are what define. So we define a set of operations that model Java, and we specify what those operations mean in that. And we say, well, an instance of a code model for a Java program is all these things with Java operations in them. And so it's kind of like LLVM bitcode, or very close to MLIR in that concept. And when you see it, so we need to model Java programs. And so that's a challenge in and of itself. And we need to model a core set of statements and expressions in there and specify their meaning and standardize that. And we can model it at a high level and low level. So we have this notion of progressive lowering through transformation. So you can pick your point at which you want the level of abstraction to reason about the code. And once we have that, we need to enhance Java reflection to give you access at runtime and compile time to access to runtime instances of these models. So, for example, you should be able to eventually do some upfront compile time checking on your model to reject programs that don't conform to your required constraints. So it's better to get an error saying your GPU program doesn't work when you compile it, as opposed to at runtime when you try to do the transformation later. So we need to allow that access both. So reflection has often been considered at runtime. We want to sort of broaden the access to compile time as well. Maybe we just focus on runtime first and then build out compile time later. Again, don't know. Still working that out. And then finally, we need APIs to build and analyze and transform the models. So that gives the ability to help generate CUDA code or help autodiff and stuff like this.
A bit similar to Hotspot, right? What Hotspot is doing behind the scenes.
Actually, it's unsurprising in some respects that the design of the code model is very similar to what a standard, more modern compiler would represent their own code as an intermediate representation. Yes, so it's like what LLVM does, like what Graal does, like what Hotspot C2 does, but it's also allowing for nested code, and that's what gives us the ability to model structure. And that's what the idea I got from MLIR. It allows you to model nested structure. And so you can capture the structure of for loops, ifs, and so forth like that, and reason about it at a higher level. When you reason about it at a lower level, it gets harder to reason about certain things, easier in other cases. And when you lower it down to bytecode, it gets even harder because all you have is go-tos. So.
But if you get, the, I don't know how well the kernel is specified, but if you know it, you could actually throw compiler errors if you already know it won't work on the
That's right.
GPU, right? So
No, that's really important. I think that's a very key thing. Going back to the example of Triton, for example, we talked about, you model tensors. You can't describe the exact shapes of the tensors statically, but you can do it runtime. But you could run the compiler analysis at compile time and say this tensor is incompatible with this one because it has this incorrect shape that we've calculated as we computed through. And so producing those at compile time, I think, is very important because runtime errors are awful like that. So they're very hard, much harder to debug. So if you can report the line number and description of information, that's extremely useful.
And would it be also useful, to know the hardware specific? So I'd say that if you have now 100 cores, that we can parallelize it differently, so we can optimize for the hardware, right?
Yeah, this is interesting because you often don't want to optimize too early in the compilation process.
Okay.
Because sometimes you don't know what hardware you're going to execute on. If you do, that's fine. But sometimes you want to delay that transformation or analysis or application of that till later when you know that you're going to target a particular GPU.
Could you have multiple stages? So no, like the generic.
Yes, you could do a generic compilation step just to do checking, and then reproduce that checks plus with other things at runtime when you know what your target
This
is.
reminds me of Leiden, right? The project Leiden, where you can decide.
Very good connection there, because we could actually do some upfront decision making through Leiden as well.
Wow.
And do some ahead of time. So there's no reason why you couldn't ahead of time generate your kernels if you knew what target you were going for. So if you knew you were going at compile time or at link time, say, to a PTX system rather than OpenCL system, you could make that decision then.
So I would say what should happen is, Oracle should give you unlimited resources, because it is. I really, this is the thing, right? I mean, if this is working, we get a really tight integration. We have the access to the hardware, and this is crucially important. And the thing is, everyone talks about AI and how to integrate that, and you cannot ignore it, for sure. I mean, this is very important. On the other hand, there is no WASM story, which is also an important thing, and this will solve it as well. And persistence, I mean, Oracle also have databases, right? And what you can have a tighter integration with Oracle. So what you could do, a crazy idea, right? If you know the Oracle optimizer, you can optimize the SQL statements from the code model
you could build
to machine code to Oracle and skip
that's interesting. Yeah, you could take the SQL and then transform it into
directly to what Oracle database understands, and then you can run Java code as .procedure on Oracle, and it will outperform SQL. So I would say, no kidding. If someone from Oracle is listening, I mean, this is the project.
It's a possibility. Yes. Yeah, I think there's, as I said, I hope to be surprised when we give access people to the prototype and see what they do with it.
The people outside, they will play and they will see lots of examples. But what's this really interesting? This is really important for the cloud and for the boring use cases, which actually generate the money, right?
You're right there.
Yeah. No, there is like the business perspective, and this is usually boring projects like how to transform SQL to machine code and Oracle database, right? So or optimized do you want to get it from community because no one likes to play with such a thing, right? Or how to generate WASM to run a subset of something. So this is also like very important, but maybe someone from community, I will see lots of shiny use cases which are less relevant for the enterprises or for cloud, right? So this is usually what happens in such projects. Let's see, but yeah. So I'm really delighted. I would say this is what I waited for. So why Java is do nothing here in this area? Because there was Sumatra and what the other projects we heard about it. Every Java one, there were keynotes, but now something happens, and I already look at the code model and code reflection, and for me it was the use case first not clear. It's like it's cool that we can actually generate. We use for me it was like code reflection, like reflection for source code almost, that you can generate code via API, right? Which is also very interesting. But now the use case is more appealing to me.
That's right. Yeah, I mean you can do that too. You can build code models directly, but the real power is the compiler producing something for you that in an easily digestible form. I just share another project. This really one just uses Panama and a native linear algebra library.
Mm-hmm.
This was used to implement. We implemented an algorithm called MSET, which is classic linear algebra, and we use a native library called Bliss.
Mm-hmm.
And we built a wrapper around memory segments to represent matrices.
Mm-hmm.
And I'm really interested in pursuing what it means to support matrices and ND arrays in the platform as well, because I think that's a key missing piece that we need to look at. But the thing is, I can combine this with code reflection, because what you can, when you operate on matrices, you may want to say, I want to do an element-wise operation, but I'm going to specify that operation as a lambda expression, because I don't want to do add, sub, all these methods, in there. I want to express it as a little expression, as a lambda expression, and I can use code reflection to sort of crack open the code of that lambda expression and then compile a kernel to do that matrix element-wise operation. And that kernel could be vectorized in the CPU. It could be multi-threaded plus vectorized, or it could be a GPU kernel using the GPU APIs that we develop. So I'm trying to connect it to a use case where someone passing a snippet of code,
Mm-hmm.
we need to optimize it. Because if the user passes in n numbers of different lambda expressions, the C2 compiler will not optimize that at all. And it won't optimize it for accelerators or for vectors and so forth.
And to my knowledge, metrics operations are crucial for neural networks, right?
They are for AI. So this example here, this library here was used to develop a machine learning algorithm, not a deep neural net, but an alternative machine learning algorithm called MSET, which detects anomalies, statistical anomalies in time-based series data. For example, it was originally developed to detect faults in nuclear power plants, but you can easily use it to detect faults in aeroplanes, when you're sampling time series data. So it's a very straightforward algorithm with some clever twists to it, but we can write it really efficiently in Java using a very efficient native linear algebra library. And then I can pound on code reflection onto that to make it even better API.
I'm really curious, and there's lots of fun, to spend some time as a Java developer, because the interesting part is now we have something like a perfect storm. No kidding. Because we know Java 21 LTS is great, so I really still enjoy it. So we have almost pattern matching, but we have the Java records, we have the instance of pattern already. I almost forget what we have, because I use it Java 17, Java 21 all the time. So I don't even know what the diff to 11 is anymore, but it's lots of great stuff, and you can write concise code.
Yes.
Data-oriented programming, right? So this is the idea that you can pass Java records, through and react to the data and keep this separated. And now this code model also plays well, because it's also separated, right? So I can the input data, react to it, and maybe call different models even, right? Depending on my business object type, I could call this model, and this model is very similar to LangChain, what they are doing. And this is with core Java. This is always important to me. Just try to minimize external dependencies and rely what Java provides. This is less hassle with updates and with versioning. So this, I would say it's really great. I'm really surprised how far you are actually, right? So
it's still a long way to go.
Yeah, sure.
So we're making progress. This year, I'm really looking forward to progress on Valhalla. It's getting closer and closer, and I think with pieces of Valhalla, we'll be able to design APIs we wouldn't have thought of doing before, because the cost of boxing starts to go away. And I think that means that we didn't want to sort of create boxes on the fly and boxes of boxes and so forth like that, but the cost of that's going to go down.
So, but the Valhalla is like a struct in Java, right? So have a really
kind of.
Yeah.
It's more a value type. It's an immutable piece of information, kind of like a record. You could view it as something, but it's a bit more general than a record. But I expect most people, when we have Valhalla, will write value records, because they offer a lot of value for performance and so forth. But I think there'll be less hopefully less complaints or less resistance to using the box primitive types to a certain extent, because the cost of boxing is going to get cheaper, which makes you rethink your API design around supporting references and primitives. And we may have an evolution story, so when I have to refer to my box primitive type, but later on I can refer to the type I want to refer to, which is int, not integer. We may have a compatible story to get to that point, which means we can start experimenting with matrix and ND array-like APIs earlier, and just deal with the box types, but have a story later to get to the primitive types underneath if we want to express it. And memory segments will give us a way to represent on and off heap data uniformly and efficiently.
In which APIs are you actually involved right now? So in Babylon and what else?
I was heavily involved in reviewing a Panama APIs and using those. I'm mostly involved with Babylon right now, getting that up to speed, launching that. So that's my primary focus for the next couple of months, I'd say.
But I think we covered Babylon well right now. So as our intro is good enough, right? Because I would like to invite you back, of course, and talk, about all the surroundings APIs and promote it, and maybe I find some user stories from use cases from my enterprise boring world, and this is what I'm interested the most. And you give me the ideas what you are doing, because if you are now explaining what happens, I immediately see what you could do with it, in the enterprise world, because it will happen. In next 2 years, the most asked question is now how we integrate, all the machine and learn models with Java, and can we also do something with Java or not? This is like, you won't believe what happens. I saw already projects which run serverless function in Python because they thought Java is not cloud ready or whatever. These are like crazy stories. And if we provide some appealing use cases or examples, this is the missing part. You say, look, you can do serious stuff with it, and energy efficiency is huge in Europe because we are forced by law, to at least show where the CO2, what happens with it. So there is like and law this year. So suddenly you have to to show what you are doing in the data center, and if and if Java will run. So I don't know whether there is a paper from Google, efficiency, performance, and energy efficiency of Java comparing to other languages. And Java is number 5. I don't know the exact ranking, but it's like C, C++, Ada, Rust, Java, and everything else is worse. So Go is slower and worse, and Python and Ruby are really bad. So it's like 35 times, and this makes Java is back in the game. So not back in the game for me, is always in the game, but it is really appealing to start with Java now.
Yeah, that's interesting to hear.
Thank you. What I will do, I will put your presentations to the show notes, and I'm really looking forward, to the next conversation. Maybe your progress with Babylon really interests me. What are the features and how it works, and also the listeners, of course. I'm pretty sure, and also Panama is also really important because I had several cases, last year how to integrate with JNI with external libraries, and this is not fun. And I was not ready. I could use JNA, this JNA, and and lots of going on. And I don't know whether you're also aware of Tornado VM, also interesting project.
Very much so. Yes, very much so. So they're very. Hopefully, we'll be able to collaborate with them on Project Babylon. And,
we already had a podcast with them as well. Also, a really extremely interesting project. They can also run on GPU or CPU, and lots of happens. Yeah.
So we'll be collaborating with them. So it'll be good fun.
Perfect. Where people can find you if they
OpenJDK list. I stopped using Twitter, to be honest, given what's going on there. So I'm not on Mastodon yet. So it's mostly the OpenJDK list right now. And maybe I should go onto Mastodon, some server somewhere, but I haven't done it yet. But to me, it's a bit sad that Twitter has gone the way it's gone. So I just stopped. I just stepped back from it.
Sure, no problem. So thank you, and thank you for your great work. It's really nice.
Thank you. Appreciate it.